Yeah, so my name is Jerald. I am a postdoc that just started beginning of the year working with Doug. I defended my dissertation in December. So originally, I was going to try to use this opportunity to give like a mock job because I will hopefully be on the academic job market soon-ish. But to be honest, I didn't quite get a presentation that I liked done in time. So what I'm going to do today instead is I'm going to kind of give my defense light talk. I'll talk about the research I did during my dissertation at a kind of a high level overview. And then I also, if we have time, I want to take the opportunity to kind of describe the work that we started working on here. It's not at all related to redirected walking. And I would like to get feedback and input if people are willing to do that. So there will be time at the end for questions and comments on both of my previous research and what we're doing now. But also feel free to interrupt me at any time and ask questions. All right, cool. So that's like a 3-4 second delay. Okay, so my research has almost entirely been involved with locomotion virtual reality. How do we allow the user to actually navigate the virtual environment they're in? And there's lots of solutions. This is considered one of the quote unquote grand challenges of VR. And the problem is that there's not really any silver bullet method. Every solution has its own pros and cons and should be used in appropriate context. Two of probably the most common solutions, at least in commercial applications that you'll see are on the left here, teleporting, where you can just point to some point in the virtual environment and then click a button or somehow tell the system that you'd like to be there, and then you just kind of show up there. This is really nice because it's quick, it's fairly intuitive, it's easy to learn, but it has one major drawback in that it doesn't allow the user to really have a good sense of understanding of the virtual environment. And on the right, you have what I've always called flying or joystick control, where this is, again, very familiar to people who have played games before or who are other types of input systems, where you can use a joystick to control your virtual point of view. And for this one, the major drawback is that it's been shown to cause simulator sickness in a lot of people, if not most people. What I'm really interested in is natural locomotion, where we actually allow the user to walk through their physical environment in order to translate and rotate their virtual representation. There is a fairly major drawback to this, though, and that is in the physical world, we're bound by obstacles and walls. And this isn't usually accounted for. And so because of this, natural locomotion, I would say, is hesitantly used as a locomotion technique at best. The other problem with natural locomotion, and because we're bound by those physical obstacles and the boundaries, is we often want to explore a virtual environment that's larger than the physical environment that we have available to us. And this is what redirected walking seeks to solve. So this is the original example of redirected walking by Redirection in 2001. And you can see in blue is the virtual path, or what he calls the perceived path. And this is a zigzag path. And the red is the actual lab environment that they use to do this experiment in. And you can see that they were able to fold the virtual path into a much more compact physical space. And so that is the key idea behind it, is to separate the physical and the virtual paths and then try to optimize the physical path in order to fit into the smallest available physical space. Another very popular technique in virtual reality is this notion of physical interactivity. A very common example is passive haptics, where if I'm in the virtual world and there's this cylindrical item I want to interact with, I can reach out and grab the cylindrical item and feel it and move it and feel the heft. And it just adds a lot more presence and interactivity with the experience. However, redirected walking breaks this. With redirected walking, you can't really do physical interactivity. And that is the main thing I wanted to tackle in my dissertation. So I'm going to go through how I did that. First, we have to kind of understand how physical or how redirected walking works. So for redirected walking, we implement what we call gains, and there are 3 of them. So the first one is translation gain. So as the user walks in the virtual environment, or in the real environment, we're going to scale their virtual walking, their virtual translation, either up or down. Similarly is rotation gain. So instead of the translation, we're going to scale their rotation either up or down. So for example, if the user were to rotate 180 degrees in the real world, as you can see here, a rotation gain of 2 would mean that they rotate 360 degrees in the virtual world. And then finally, we have curvature gain, which is a bit different. So for curvature gain, as the user walks in the real world, we're going to rotate their point of view just a little bit in one direction. And subconsciously, they will correct for that by rotating their body in the opposite direction because they want to maintain a specific line that they're walking on. And if we throw all of these together with some sort of intelligence, we can use what we call redirected walking algorithms to decide what gains to apply when, and we can have an experience that will hopefully be more immersive and more exciting than if they were to use some other navigation technique. That's the goal. Unfortunately, these gains only work up to a certain extent. So a lot of the research in redirected walking has been in determining how much we can apply these gains before people start to notice. And so that has been kind of the big cutoff, at least up until maybe a year or 2 ago, is we want to make sure that people don't notice. And so a lot of research has gone into determining, like I said, how much we can do this for. And I think there's more interesting research that can still be done in this area that I'm potentially interested in doing. But for now, these are the numbers that almost all redirected walking researchers use. So I said that redirected walking breaks this notion of being able to interact with the physical environment. And to understand why that is, I have this little graphic where, so if they're, so if they're just wanting to interact with a physical environment, they're not in virtual reality, they just walk up to the object, right? And then interact with it. However, sorry, I don't know why my mouse is. However, in virtual reality, we don't have one environment that we're concerned with. We have both a virtual and a physical environment that we need to keep in mind. And with just plain natural locomotion, that's still okay, as long as the user and the virtual object and physical object share the same relationship, they can still interact with it. But as soon as we start to add these gains, everything breaks. And you can see, so here's an example of curvature gain, right? Where as the user walks up to a virtual object, we're applying these gains. And what that's doing is adding discrepancies in the mappings, the relationship between the virtual user's pose and the physical user's pose. And so to solve this, or not solve, to address this, I guess, I introduced what I'm calling environmental alignment. To start, I'm going to just kind of go over a bit of terminology so we're all on the same page. So a pose is the user's position and orientation in 3D space. For redirected walking, because we're only really concerned with their relationship with the azimuth plane, we can reduce that to X, Y, and theta instead of needing a 6-dimensional pose. I'm going to call a mapping as the relationship between the physical and the virtual pose. And I'm going to go ahead and call what I call the identity mapping, which is a mapping where the relationship between those two is equal to the relationship between the two ordinals. And so if you have an identity mapping, then you can do this physical interactivity. That's kind of that's the requirement for a mapping in order to interact with physical environment. And alignment is the process of using redirection to achieve a specific mapping, and specifically environmental alignment is using redirect walk techniques to achieve identity mapping. So we're not only, so my notion is to not only use redirected walking to avoid obstacles and boundaries, but also to use it to achieve these specific mappings so we can have more interesting interactions. And with environmental alignment, we're doing so with the physical environment. So my first work looked at how we can have a more intelligent, what I'm going to call reactive redirected walking algorithm. So to get started, we have to kind of talk about these algorithms. There are generally considered categories in two areas. We have reactive. The reactive algorithm has no knowledge of where the user is potentially going to go. They're usually a greedy approach that relies on a very simple heuristic. On the other hand, we have predictive algorithms. So they have some sort of knowledge of where the user might go. This might be, perhaps they have a complete virtual path known ahead of time that they expect the user to walk down, for example, in a tour type experience. Or maybe they're in a more constrained environment where we have some sort of prediction mapping to understand where they're probably going to go. These, when applicable, are usually outperform reactive algorithms, but reactive algorithms are much more generalizable. They can be applied in any situation, although in some situations they're not going to be as effective as predictive algorithms. So for this work, I chose to focus on reactive algorithms and kind of create like a baseline from there. The two state-of-the-art algorithms for reactive algorithms anyway was steer to center and steer to orbit. And again, I mentioned that they kind of rely on this very simple heuristic. And for steer to center, we're just going to apply whatever gains we can apply in order to try to get the user to get to the center of the physical environment. And steer to orbit is similar, but instead of getting them to the center, we're going to try to get them on a path that orbits the center. And these are fine and great as long as we follow some certain assumptions. So if we have an environment that has an obstacle, say in the middle, then this would break, obviously. Or if we have an environment that has non-convex boundaries, then it could break. And so I wanted to see if we could figure out a way to create an algorithm that can generalize a given environment and pick the best steering location instead of relying on a simple heuristic such as the center of the environment. To do this, I went ahead and borrowed some techniques from robotics, the main one being artificial potential functions. So quick primer, artificial potential functions is an interesting kind of abstract mathematical function where you have some sort of domain. In this case, it's going to be the X and Y axes of the physical environment, and then some sort of range. So in this case, in this image is the Z axis. Generally, you want to create, or the goal of a system is to be in the lowest possible energy state, so to be at the lowest value on that range. And then obstacles and boundaries are modeled to be on the highest point of that function. So an example might be if we have a physical environment that's say a square with a large square obstacle, we can create an artificial potential function service that looks like this. And from that, we can generate a gradient field where the arrows should always point in the direction that is most advantageous for the user to be. So at any given point, we can reference this gradient map and be like, okay, that's the direction I need to steer the user, instead of, again, simply just saying steer them to the center. This is the equation. I'm not really going to go into how this works. The important thing to know is that there are two components. There's an attractive component that will pull the user towards a specific location, and a repulsive component will push the user away from specific locations. And so together I call this the push-pull reactive algorithm, or P2R. one important thing to note is that we're going to assume that we can't that redirected walking won't always work because we are bound on these perceptual thresholds, these gain values, and we're going to assume that we're not going to exceed them when we apply redirected walking. There will be situations in which the user will walk into a boundary or an obstacle unless we stop them. And so that's what we're going to call a reset. So as the user approaches a boundary, we're going to stop them. We're going to have them turn towards a more advantageous position, and we'll send them on their way to continue their experience. Obviously, this is very jarring, or can be very jarring to the user. It can break the experience. And so because of this, the number of resets encountered for a given virtual path is the main metric we use when comparing different redirected walking algorithms. Okay. For the sake of time, I'm not going to go too deep into the evaluation for this. Mainly, so the important thing to note is that we use simulation-based evaluation. The main reason being is that it's very hard to get the number of trials that we need with a human subject study. And because we know what the perceptual thresholds are, with a large caveat, we can go ahead and say that simulation can give us at least approximate knowledge of how different algorithms will compare against each other.
Did you implement it though for people to be able to experience firsthand, even though you didn't do human subject studies?
I didn't. There's a lab mate that did, but yeah,
Okay.
there's a demo somewhere. It's not very. It's not that much more interesting than any other redirect walking demo because all of what it's doing is kind of behind the scenes.
Mm-hmm.
It feels like any other redirect walking demo, other than you just might have a few fewer resets.
Well, right. Well, I guess the reason I asked is because I wondered if this gradient-based approach, it tries to steer you in kind of different directions all the time. Like the direction that it's steering you can change constantly.
Yeah.
I wondered if that would change the experience that people have.
Yeah. So that also can be said of the steer center, though probably not necessarily the same degree.
Mm-hmm.
And there has been a little bit of research, and there definitely needs to be more research to show how changing redirect walking gain rapidly can be noticed. It's more easily noticeable than just the redirect walking gains themselves.
Or disorienting or threatening or whatever.
Yeah. So yeah, big caveat on that is that that's something that should be more evaluated. These are the three environments that I decided to test. So we have our basic kind of square environment. One thing to note is that all of the arrows point toward the center. So we kind of expect this to behave just like the steer center. And then we have a couple more complex environments. And the results that we got for that were just as expected. So on the next few slides, we'll have two graphs. On the left will be the number of resets, and on the right will be the average virtual distance traveled per reset. So it's kind of just two different ways to talk about the same metric. On the left, lower is better. On the right, higher is better. So for the environment with nothing in it, we would expect not much of a difference, and that's exactly what we saw. As soon as we started making the environment more complex, though, we started seeing a much better results. And then for this one, environment C, which was admittedly the worst case scenario for data center because there was an obstacle in the center of the environment, we saw a much larger improvement.
Can I ask one more question?
Yeah.
So it's similar. It follows up from my previous question about the user experience of being steered in different directions constantly.
Mm-hmm.
And so if you're making the assumption here with these graphs that resets are the thing to avoid at all costs.
Yeah.
But I wonder if there is a point where the redirection that's happening continuously is so disorienting or sickening or whatever that you would actually prefer to kind of walk straight and then do a reset. Has anybody studied that?
So again, I think the community has kind of made this assumption that as long as they don't notice it, then it's fine. So again, with this work, the smoothing may not be exactly as perfect as it would need to be in the actual real world implementation. But if we can assume that they don't notice it, then the community has assumed that preference, or that they wouldn't need that break, I guess, or that they wouldn't, they would prefer to have fewer resets. And again, that is something that I think largely the community has disregarded, is kind of users' preference in these experiences. So just recently, research has started to look at, well, maybe it's better to apply more of a gain if they notice it, but it keeps them from having a reset. Or
what I'm saying is that maybe it's okay to have a reset,
right,
if I can stay in the environment longer and I don't get sick.
right. As far as I can tell, redirected walking doesn't add any more simulated stiffness than just natural locomotion, if done properly. And that, again, that's a big, if done properly, is doing a lot of lifting there. But that, at least that's what the research kind of points to. And one of the big bonuses of redirected walking is that it still maintains a lot of those benefits of natural locomotion, such as the reduced simulated sickness as opposed to some other methods.
I have a quick question.
Yeah.
What was obviously the minimum is 0 redirection, but what was the maximum redirection you were allowing in this?
So yeah, there's a 2010 paper by Frank Steinke, Hamburg University of Hamburg, where they determined what these values are.
So you just used
Yeah, and that's pretty much everyone in the rear walking community just uses those numbers. So for example, for rotation gain, I think the upper level is like 1.28, and the lower level like 0.84 or something like that. So it's not that much that we can get away with. There's also a lot of interesting research that still get to be done in that. So there's some research to show that people will adapt to it, and you can start to apply more redirection as the experience continues. But we haven't really explored that yet. Or there's other research that there might be other ways that we could have the user obtain more redirection without noticing. And there's also a lot of research, or one research paper to suggest that it actually could be very individualized, and instead of creating these set values for all of the entire population, we should be trying to come up with ways that we can quickly measure for each individual and use each individual's own values. So. All right, so that has nothing to do with interacting with the physical environment. That had more to do with avoiding the physical environment. So that's going to lead me to this next bit of work, where I actually start to implement these reactive alignment. And I had to go over that first paper because this next paper builds off of that. So as a reminder for that first paper, this was the equation. One thing I didn't tell you though is that we didn't actually use that attractive component at all. We just used the repulsive component. We were just trying to keep the user away from boundaries and obstacles. And so now this work, we're actually looking at re-adding that attractive component in order to achieve other things than just keeping them away from boundaries and obstacles. So with just repulsive component, this is what a potential function surface may look like. And if we were to add an attractive component, it might look like this. One thing I want to mention is that this is a bit misleading, because I mentioned that the potential functions work on an n-dimensional domain, and for the previous work, that domain was just the physical environment. But now we want to do more interesting things, and so now the domain is going to be what we call a configuration space. So a configuration space, and another technique borrowed from robotics, is an n-dimensional space where each dimension represents a particular degree of freedom, traditionally of a robot. So for example, an iRobot Roomba would have a 3-dimensional configuration space. It can go X and Y, and it can rotate in theta. And any particular point in that configuration space will represent one unique configuration of that robot. So one unique position and rotation combination. So what we're interested in is actually using the virtual environment and the physical environment together in order to achieve this alignment notion, right? So the configuration space that we're going to work with is actually 6-dimensional. It's going to comprise both the physical and the virtual environment and the user's physical and virtual rotation. The idea being is that we can find points within this configuration space that satisfy those requirements for the identity mapping. And we can call those goal configurations. So if we can reach those configurations, then we are in a point where we can interact with the physical environment. And so we can use any host of robotic pathfinding or navigation techniques in order to find a path from the user's current configuration to those goal configurations. So one of the studies that was out of this paper that I think is probably the most interesting was asking the question, can we use this notion of reactive alignment to effectively reverse the effects of redirected walking? So can we apply redirected walking to a user for a fit and then undo those effects with this alignment and get them back into an aligned state where they interact with the physical environment? Again, I don't want to spend too much time going into the weeds of the methodology. If we want to talk more about it later, I'd love to. The main way that this experiment worked, again, it was simulation based. And what we did was the simulated user would start at the origin of both the physical and virtual environments. And then they would walk in a random direction for either 5, 10, or 20, or 30 meters, and then turn around and walk back. On the return path, there would either be, sorry, I should preface it. On the way out, they would be experiencing traditional redirected walk. So they'd be told to avoid the boundaries and obstacles, essentially. On the way back, they would either experience the, again, traditional redirected walking, or it would be switched to the, what I call the alignment redirection, where we'd be trying to not keep the user away from boundaries and obstacles, but to bring them to this target alignment location. So those were the conditions. Let's see here. And what we found was, so on the left, we have the positional error for the no alignment condition. On the right, we have positional error for the alignment condition. So the positional error is how far in that Euclidean or in that configuration space, what was the Euclidean distance between the goal configuration that represented the identity mapping and the final configuration when they got back to where they're supposed to be. So an error position of 0 means that they are perfectly aligned and they can interact with the physical environment. What we found was that with the no alignment condition, there was no significant difference between or within that condition, which we kind of expect, right? If we're just applying regular avoidance redirection, we would expect a somewhat random distribution of the errors. And when we did apply alignment, we found that sometimes it worked fairly well. So you can see that 10-meter inflection, or that 10-meter distance, the median was pretty close to being completely aligned. And there were some outliers. But as you got farther away from that, we actually ended up being worse. And so we can look at that more closely. I should have just got rid of these animations. That's just to show that we had significance. And it's taking a while to load. But we showed that for some reason, this 10-meter condition performed way better than all the others. And so, well, one, we learned that when alignment was not being applied and just the avoidance redirection, again, there was no significant difference. So, but when we did apply, the 10-meter alignment error was significantly lower than all the others. And so what we learned from this was that there might be some ideal virtual distance when you should switch on the alignment redirected walking if you want to try to achieve this alignment condition. That didn't really sit well with me though, so I did a bit of post hoc analysis of what was actually going on. And what we found was that that's not necessarily the case. Instead, that there's this set of conditions of the relationship between the goal configuration and the point of the configuration of the user at the point which you start applying this alignment that need to be met in order for alignment to be achievable. And it just so happened that that 10-meter condition most of the time satisfied those conditions, or was very close to satisfying those conditions, which is why that particular condition performed as well as it did.
Can I clarify something?
Yeah.
So on that last point you made,
Yeah,
you said there's a set of conditions required for alignment to be possible. I guess what you mean, tell me if this is right, is that, I mean, alignment is always possible, but if you're gonna respect the.
Correct.
The thresholds for non-detectability,
right.
it's not always possible.
Correct.
Okay.
Yeah.
Gotcha.
And then there's some very potentially interesting future research records that we're taking from this. So, for instance, we talked about resets and how we use that in order to avoid users from walking into a boundary. But maybe we can also use resets at other points to do other things. So maybe we can take the hit on that break of presence for a bit if it means that we can achieve this alignment. Or maybe we can try to introduce some other types of resets, like a positional reset, where it's similar. You pause the experience, but instead of having them rotate, you have them move over to a different location, and then you can continue the experience and you'd be quote unquote aligned. So there's a lot of interesting research that could be done still on that, down that avenue. And then finally is this notion of predictive environmental alignment. So the second paper I talked about was looking at this idea that we can use redirected walking techniques in order to achieve the goal of allowing the user to interact with the environment, but we're doing so in a purely reactive way. And what we kind of found with that is, just like with traditional redirected walking, the reactive approach is the most generalizable, but it's not going to always produce the best results. And so we thought it'd be best to look at this from the lens of more of a predictive algorithm in order to achieve true quote unquote alignment. So predictive algorithms can be broken into two different categories, roughly. Dynamic planning algorithms will make predictions based on some sort of probability of the user's current state and the virtual environment. They usually require a more constrained virtual environment. So for instance, you could be walking in an office building, in which case the system will know, well, they're probably either going to go ahead or backwards or go into that room. And based off those options, they can come up with some sort of probability model and then make predictions from there and apply the redirected walking techniques from there. Further down the spectrum is this notion of static planning, where we can make predictions based on a predetermined virtual path. This is the most constraining experience, but we can achieve the best results from it. And so when I first started planning out my dissertation, I'm like, okay, we're going to do the static planning. The example there, copper, was created by an older lab sibling, and so I'm like, okay, I'll extend that and make it work. But then I kind of came with this other cool notion that continues this theme of borrowing from robotics, and that's using inverse kinematics to solve the problem. So as a refresher, inverse kinematics is the inverse of forward kinematics. So you would have what's called a kinematic chain. So a kinematic chain consists of a series of linkages and joints. And if you know the position of the first joint, what we're going to call root, and the length and the rotation of all the linkages and the joints, you can forward propagate to calculate where the last joint, what we call the end effector, is. So why would you want to know that? Say you have a robot arm and you need to know where in 3D position that robot arm is. and you have sensors on all the joints and you know the length of all the segments, you can calculate very precisely where that point is. The inverse of that is, say we have this robot arm and we want it to be in a specific position, and we need to know what the rotation or what the joint angles and possibly the length of the linkages, if that's something we can modify, need to be in order to achieve that. And so with that, you can, here's like a 2D example, and we're gonna stay pretty much in the 2D realm for this use case, because again, with rear walking, we're only concerned with that as a plane. So assuming that there is a target physical location, that there's a known virtual path that consists of straight segments, and we're going to only be using translation and rotation gains, we can make these analogies. So a kinematic chain is a series of rigid bodies connected by joints, and we're going to say that that's analogous to where the initial conditions are defined by that known virtual path. The root is the start of the kinematic chain, and we're going to say that that's analogous to where the user starts in the physical environment. The end effector is the end, and again, that's going to be analogous to where the user ends their path. So after they've walked through the virtual path, where they are physically in the environment. A revolute joint is a joint that can rotate within specific constraints, and we're going to say that that's analogous to rotation gain. And a prismatic joint is a joint that can elongate within or shorten within specified constraints. And we're going to say that's analogous to translation. So what that might look like is, say we have the virtual path here on the left, a path that is going to be consist of what I call segments and waypoints. Oh, okay, bye, Sam. So we have, so the example path here on the left has 4 waypoints and so 3 segments. And on the right, we have the corresponding physical path. So my little guy there in the bottom left is representing the starting location. We have X in the top center that represents the target location, and we need to find the redirect walking gain values that result in the path ending in that target location. So for the most part, in an ideal world, like cool, just throw an off-the-shelf redirect walking, or no, sorry, inverse kinematic algorithm at it, solve it, call it a day, get 3 papers out of it. Unfortunately, one thing that we have to contend with, and that traditional inverse kinematic algorithms don't, is this notion of resets. So if the only path that could satisfy all constraints would exit the physical environment, well, we can't actually have the user exit the physical environment. And so what this would result in traditional IK scenarios is like an insolvable situation. Like there's no solution for it. Sorry, you're out of luck. But we can implement resets, in which case, in this example would look like essentially just adding another joint at where the path would cross the boundary, and then essentially resolving from there. And so that's kind of one of the bigger contributions of this work was this notion of using IK as a base, but then kind of extending it to satisfy these reactive walking requirements. So the research question I had for this was, does incorporating passive haptic feedback into a reader's walking application improve the user's experience? Because this is something that hasn't been done before because it couldn't be done before. However, this was pre-pandemic, and then the pandemic happened, and so we decided to pivot. We could have gone to just another simulation-based approach, but at this point, we're kind of determining that while simulation definitely has a strength, there are definitely parts of it, parts of the research that it just can't address. And so we wanted to definitely stick with a live user subject study for this. Also, my committee told me I had to. So what we pivoted to was, instead of looking at the user experience, we noticed that these virtual experiences that are using iterative walking, they have a designer. And so how can this tool improve the designer's experience? So a bit of tangent on that, redirected walking authorship. So these algorithms are very difficult to develop or integrate into applications. And because of that, it really hasn't been adopted by the industry. There are other challenging VR techniques that have evaluated interfaces to aid the designer in the use, and because of that, we've seen greater industry adoption. So this is, as far as we can tell, the first work in the entire history of redirected walking to actually evaluate an interface specifically for the designer and authoring redirected walking experiences. And so I think this is potentially a burgeoning field of research or direction of research that I think has a lot of potential interesting outcomes. So off my soapbox, back to the experiment. We had a total of 70 participants. The requirement was that all of them had to have at least 1 year of experience using Unity for VR development. So we didn't want to be teaching people Unity as they're using this tool. Most were from academia. 2 of them were from industry, and they were recruited from online communities. This was all done via Zoom, where I would watch them perform the task, and we'll actually get to see what that task was in a bit. So for the methods, participants were tasked with finding participants were tasked with finding a physical path for a given virtual path that met all the requirements. So they had to maintain the game thresholds, and it had to end in a specific physical location. And their secondary task that they were told was to minimize resets. So they were told that very explicitly. Their primary task was to find the path that satisfied those 2 other constraints. While doing that, try to minimize resets. There are 2 modes. So manual mode, where each user had to set the gain value of each segment individually, and automatic, where we had the environmental alignment IK algorithm try to set the values for the user. And there are 3 conditions of path difficulty: easy, medium, and hard. And over here. Oh boy. Is that it? No. Sorry, I'm on a different workspace. So an example, our user using the interface that I developed for Unity. The green path is the virtual path that they have to solve for. So you would imagine that, like, in an actual use case of this, there'd be an actual virtual environment with a known path. And then we overlay an example physical environment. So here the user is manipulating the user's starting position and rotation, and they go over and manipulate the gain values, and those are bounded so that they can't go beyond the thresholds. And then once they get the end of the path to that target, that finish button lights up. So that was the manual mode. Oh no. Okay. And here is the automatic mode. No, this is the So here you can see all they do is they manipulate the user's starting position and rotation. And then the IK algorithm will select the gain values. And you can see over there on the right, the gain values kind of move around and then try to select gain values such that it solves the problem for them as they move the 1 degree or the position and the starting position rotation of the user. So we looked at two types of metrics. So we had a set of quantitative metrics where we recorded the time it took for each condition. And then we also had them complete the NASA TLX and the system usability scale after each block. So they would experience easy, medium, hard of either manual or automatic. And after that hard one, then they would do the NASA TLX and the system usability scale, and then go back and do the other. After it was all done, there was a series of semi-structured interview questions that I asked. And then also they were asked to do a talk aloud during the actual experiment phase of the experiment while they're doing each task. For the quantitative results, we found kind of an interesting find. So for the easy one, the automatic mode was a lot faster. But as it got harder, it actually became harder and harder to use. And so that became slower. So we see this kind of inverse in trend. And then for resets, we found that the manual mode could produce fewer resets. And that was, again, just because they had more control over the entire system. But in general, resets, at least for this experiment with the simplified conditions that they had, did not really seem to change that much significantly, except for in that hard condition there. So a bit of going over the qualitative results. Again, each participant had 2 data sets. There was a think aloud portion of each trial, and then there's also semi-structured interview at the end. The recordings were analyzed at a 2-step process where we would first code as we kind of listened or read through the transcript without really thinking with a greater context. And then we go through again with our codes and try to find larger patterns and trends. There's a specific word for that that I have not been able to think of all day. There's a specific term for that particular style of code, but also I don't know how to Google that. So we found a couple trends that I kind of want to go over. So the first one is in communication control. So what we learned was that authoring interfaces should allow the designer to decide how much control they have instead of just saying, sorry, you have to do everything yourself or you don't get to do anything. The system will do it for you. And the authoring interfaces should communicate very clearly with the designer what their intention is, what they're doing, why they're doing it. We also found some interesting in this category of flexible integration of the automation. So we learned that participants would prefer to use a combination of the automatic and manual mode. And they would like to be able to choose where each mode gets applied. So for example, some people thought it'd be best to use automatic at first and then use manual to kind of fine tune the end point. Some people wanted to get the opposite, where they I'd like to use manual first and kind of get it in the rough ballpark and then use automatic to just kind of snap it to where it needs to go. So what we took away from this study was that using this automatic mode was more effective with the shorter paths, but not so with the larger paths. And most participants mentioned that somehow combining the two would be optimal. One thing I like to point out is that this was what I would consider an exploratory study. The actual algorithm that was implemented was not optimized, for example, for resets. It was only optimized for trying to get the target to or get the end of the path to the target location. And it wasn't using the most complex IK algorithm out there. There's also a lot of other ways that we could add resets to these IK algorithms. And I'm not sure if the way I went about it was the best, looking back on it. Another thing to point out, so this was all looking at static planning, where we know the entire virtual path ahead of time. But if we want to implement something like this in dynamic planning algorithms, where we only know a portion of it, and we want to try to achieve environmental alignment from that point on, they're gonna have to rely fully on the automatic mode, because there won't be a designer be like, okay, pause, I'm gonna go figure out what. And so we have to make that better for that to be more effective. And then finally, more study regarding authorship of these experiences would be required. Cool. I want to just quickly talk about what that took longer than I intended, I'm sorry. Quickly talk about what we're doing here. So I'm looking at, with Doug and Sang, AR facilitated remote brainstorming. So the notion being brainstorming traditionally is a very collaborative and very in-person and physical thing. And with pandemic and just this kind of move towards more remote, more virtualization of work, we started looking at doing this in a completely virtual way. And while this definitely has its own benefits, we feel that there are improvements that can be made in order to make it more like traditional co-located brainstorming sessions. And so that's what we're kind of looking at a high level. How can we make this remote AR facilitated brainstorming feel more like the traditional co-located brainstorming? And I think the answer that we kind of come up with is to try to reintroduce physicality to it. So for example, session might have, we might have 2 users in 2 different locations, and they might have an in-sync brainstorming session. One user would then add a sticky note, and then the system, the AR system that we're implementing would tell the other user like, oh, there's a new sticky note here. Maybe you should add one there. Or if they wanted to potentially, one user were to move a sticky note, right? The system would highlight that and be like, oh, other user moved the sticky note. You need to move it if you want or to maintain or to be in sync with the other user. We think that this might have several benefits, such as kind of making sure that the users are actually mentally in sync at all times, as well as physically in sync. So the enforcing this make sure that they are physically in sync would help them to make sure that they're on the same page as far as the brainstorming goes. And a few other benefits. And I would love to hear any feedback or thoughts that you have on this kind of high level thought. And Doug, if you have any other things you would like to add to that, feel free to go ahead. But yeah, that's my talk. We have a couple more minutes for questions and or comments if people